I want to make sure I explain this correctly, but more importantly, I want to make sure that an assembly of charges is the work, the energy of an assembly of charges is the work done in bringing each charge to their location. Go ahead, Ella. Can't see it. This has been a thing all day, all week. I might need to get, I don't know.
Mr. Bright is running into the same issue. Like the Wi-Fi cuts for a second and then it disconnects.
Whenever this let's see. Oh. Yeah, that's what I'm going to try to do. So what we're really trying to do is calculate the work done in assembling the charges. And that's quite literally, if we break it all the way down to its most basic form, we are doing this calculation over and over and over again. Now we have shortcuts to do that, but you could use just this and do the math here. So I'm going to refer to this because I think it's helpful in understanding how we deal with an assembly of charges. There's things about this, though, that you may not remember, and I want to make sure it's kind of front and center. And that is, the electrostatic force is a conservative force, which means that it is path independent. So when discussing the assembly of charge, I don't have to discuss the path the charge takes to get from infinity to its chosen location. Regardless of the path that it takes, the same amount of work will be done. That's one of the meanings of a conservative force. And I'm saying that not because I like to hear myself talk, although I do. I'm saying it because do you remember those equipotential map questions we've seen? Where you have the equipotential lines and it looks like a topography map? Often one of the questions there talks about what is the work done in going from one location to another. And they'll make sure that it goes in a pathway, or they'll make it look as though it's a pathway that is complicated. They may even have a multiple choice question where they show a topographical map or an equipotential map and show 5 different pathways that go from A to B and ask which one of those takes the most amount of energy. And it's a trick question, because they'd all be the same amount of energy regardless of the pathway taken. Yes?
When you talk about the pathway taken, this isn't talking about removing a charge from the system. This is talking about just moving the charge in the system, right?
It wouldn't matter. If we're talking about energy, whether we're talking about removing a charge or adding a charge, it's still path independent.
Oh, okay.
I mean, the difference might be in one case you might gain energy. So, in creating this system, you realize that we go through the process one charge at a time and assume that each charge was brought into position independently, but was done in some random order. And the order shouldn't matter. The total amount of energy that is there when we are done should be the same. Does that make sense? All right. So with that being said, the first charge brought into position requires no work to be done because there is no other charge present, which means no electric field, which means the force in that area would be 0 on that charge. So if we just assume that our starting problem has no charges here at all, and we're going to bring in one of the charges, since there is no charge presently, there's no electric field here, I would experience no force in moving that charge to any location. So I'm going to bring the 2Q charge in from infinity and place it here. And I will say that no work was done bringing that charge into place. We good? All right. I want to bring the next charge into place. And now that I have a charge in place, I'm going to bring the 1Q charge into place, and it's going to go right here because that's where I had indicated it was. Now, I can use this to make that calculation. And the argument I would make is, okay, this is also right? Force is Q times E. In the case of this problem, that's going to be and I could integrate because I know the expression for the electric field for a point charge. So I could put I didn't put, let's just say this is side length S. Now, I'm playing fast and loose with the equations. And I shouldn't. I should be very specific about positive and negative and all that kind of stuff. And I'm just kind of leaving that out. I'm bringing another positive charge next to a positive charge. It's going to require energy of me. So I'm just going to leave that to us for another conversation. I just want to remind us how we do this. Now, I'm purposefully kind of, going through this as if you would start from a fresh formal theory and work out to the end of this. But I'm also trying to point out that we know what this is supposed to look like. This ends up being just 2q over r, evaluated from infinity to s, where when I put infinity in, that goes to 0. So the only thing that matters is that we are going to be a distance s away. Yeah, I'm sorry. Yeah, I could. So this whole thing, kind of unnecessary, because we have a definition of electric potential that we've already been using to indicate the size of the electric potential for a point charge brought from a place at infinity to another place where there is a collection of charges. So you can do it the long route, or you can use this as your shortcut. Now, the reason I did all this is because you have to remember that when we're dealing with the assembly of charges or anything related to electric potential, we are assuming that the electric potential, not potential difference, the electric potential represents holistically the amount of energy required to get to a location from a location where there's no influence, which this problem requires. A change in potential is not necessarily how much energy there is, unless you start from 0 or know how much energy you had when you started. This has come up before, and it's going to come up again. So in bringing my charge here, I'll get 2q squared k over s is the amount of energy necessary to bring my 1q charge in from wherever it was to here. Now, energy adds together. So when I go to bring my next charge in, I could calculate the work done against this charge and then add to it the work done against this charge in order to determine the total amount of work to bring that last charge in from far away. Or I could recognize that I have an expression already that's about electric potential. And note that electric potentials add together. And I could calculate what the electric potential must be at this location from the presence of the other two charges. And I think you guys could do that right now. It's not particularly hard. I have the electric potential from this charge, which is 2q over s, okay. And the electric potential from this charge, which is just going to be qk over s, which means that at this location, there's an electric potential of 3qk over s. That is the electric potential at that point. To bring my third charge in, all I need to do is multiply this by the size of that new charge, 3q. And that would be the work done in bringing the third charge into place. So I get 9q squared k, out of room. 9q squared k over s. Now, the answer to the question is here, but the answer isn't yet expressed. It took this amount of energy for the second charge to be brought in place, and this amount of energy for the third charge to be brought in place. The total energy required to assemble the group of charges would be the sum of those two, which gives me what looks to be 11q squared k over s. Do everybody understand that part so far? I'll see your question.
Why did you add the, what did you get the 11 from?
Where'd I get what?
The 11?
9 plus 2?
How did you add
Okay, ready? You're gonna write it down? You already have it written down. Where did this come from?
And we were finding out how much energy it took to add the 2.
Yes. And where did this come from?
How much energy it took to add the 2?
To what was already there, right? Because there's Q and 2Q were already there. This was an additional amount of energy required to bring this other particle from infinity to here, while the other two charges were present. I can't leave out the fact that it already took me 2q squared k over s to bring in the second charge. Okay, so far? Allison?
My only question was, if they asked us and we have numbers, we would just say express in terms of joules, right, because it's energy.
It would be energy expressed in terms of joules. Yep.
And it doesn't matter what order we do it in, it would always result to an 11 QKS with the,
In this instance, sure.
okay.
But let's pay attention to something real quick. It wouldn't matter the order, but look at what you add together to get here. You realize that it's the electric potential between these two, the electric potential between these two, and the electric potential between these two. All three electric potentials get used eventually, and they're all simple sums thereafter. Does that make sense? So, yeah, it doesn't matter the order, but be aware, pick an order and stick with it. Don't forget the energy required at each step. So you should try this over again. Pick a different one to be there first and show that it works out the same. It's not hard to do this problem. I'm going to be putting up an FRQ each day. My expectation is 15 minutes of your time. And bring that, you're going to submit that FRQ online, and you're going to bring the FRQ for us to work on tomorrow. Today, you should expect something similar to this, all right?